I want to introduce the basic ideas and especially some of the terminology about maxima and minima, otherwise known as optimization. So this is a theme for our class. We've got a situation where we're running a company and we have looked at various choices for X, which is the daily production, how many widgets, well, in our case it's sporks that we produce. And we've looked at, or maybe we're trying to predict or model what the profit is going to be as a function of daily production. So if we produce 0, we don't make any profit at all. We actually make a loss because we have to spend money. And if we produce too many, we're spending too much. The factory can't handle it, pay overtime, whatever. We get back to 0 profit. Somewhere in between, we want to be, it's going to be better. So one contrast that I want to point out briefly is we're pretty used to, sort of mathematically with like algebra and that kind of thing, is finding the intercepts of the graph of a function. And looking at where is, if we have p equals, say, f of x, setting that equal to 0 and solving, that's interesting. And it's bread and butter for algebraic thinking, but it's not particularly crucial here. That's just telling us where we would barely break even and get 0 profit. It's good to know, but we want to stay very well away from those. We want to be more in this region. Where we really want to be is right here. We want the maximum profit. We'd love to predict where that maximum is going to be and then set the production value to be. It looks like 150 here. And what if our prediction is that when we set the production to 150 per day, that we get 120 profit, let's say thousands of dollars or something like that. And that's the best we can ever do. That's where we really want to be, and we want to see how calculus helps us find those kinds of points. So just terminology, though. There's a couple of terminologies for a point like this that is the greatest value of the function, and that is an absolute max or global max. Or maximum, but we often abbreviate it with max. So that's where we'd really like to be ideally. Okay. What about the absolute minimum? Well, on this graph, actually, let me not extend that. I sort of extended that without thinking. On this graph, where x is going from 0 to 200, the absolute minimum is right here. Or you can say global minimum. They're just synonyms really for us. Absolute minimum. Really important, though, is that absolute or global max or min depend on exactly the region, usually an interval, of x's that you think are relevant to the problem. So let's say it's absolutely unthinkable that we would ever have negative x. That was weird. Negative production of sporks or something. Okay. And let's say it's just absolutely unthinkable that we would ever go beyond 200. Then this is going to be the lowest that function ever gets. If you make your interval smaller and smaller, you're going to change those absolute maxes and mins. So that's relative to a specific domain, and usually in practical problems that domain has something to do with the realistic version of the problem. Now, what about here? I want to focus on this point, though. You might think, oh, it's kind of interesting that that's a little hump, but who cares? We definitely want to be over here. Let's say that value is 100. But let me motivate just a little bit why we would care about this. Looks like if I set the daily production to be 60, then I get 100, which is not as good as 120. But notice that it's better than anything around it. And so this would be called a relative as opposed to absolute, or local minimum. Sorry, maximum. We're still talking about maximum. Okay, so relative as opposed to absolute, and local as opposed to global. So either any of those 4 words are good, and you should really know them all. Okay. So why would we care about this? Well, suppose we are currently producing 60 and getting 100. Somebody comes in and says, you know, like the hotshot young intern or whatever says, hey, if we immediately change production to 150, we would be doing better. And we're just going to laugh and say, can you build a factory overnight? Can you actually more than double production overnight? It's not going to happen. Maybe in the long term we'd like to get here. But right now, this is not a bad place to be. And any small change that we made in the production would be a bad idea. And that's really what's important about a relative or local maximum. Any small change, any little local disturbance in the input is actually going to make us worse off. Similarly, this thing, let's say when the production is 120, I get 80 profit. This thing is called a relative or local minimum. Okay, it's not the absolute worst we could do. We could just shut down the factory and lose money every single day. Or we could overproduce dramatically and lose and just barely break even, make no profit. Or we could be here, or we could be here. But it does say that if we're at x equals 120, and we talk to the consultants, we believe this curve, this model that they predict, then we're extremely motivated to do something. Increase it, increase production, decrease prediction, whatever you do, because we're in a local little pit here. It's the worst possible anywhere nearby. And so those are really, really important because realistically, you often really only care about what happens when I make small changes. This is a bad place to be. If I'm allowed to make a small change, anything is an improvement. Here, if I'm only allowed to make a small change, actually anything is not an improvement. And I'd have to make a really big change to get all the way over to this absolute maximum. So we're going to be interested in how calculus helps us understand where all these features are going to be. But it's nice, first of all, to know what the terminology means.